Horizontal asymptotes come in three different flavors depending on the degree, of the polynomial on top and the polynomial on the bottom of the rational expression. And so these three categories are when the bigger degree, the higher degree, is on bottom. You have same degree, top and bottom, and you have bigger on top. So we're going to talk about what these do. So when you have the bigger degree on the bottom, the higher degree on the bottom, as in the case of f of x equals 1 over x, remember that 1 is really times x to the 0 power, and that this is really x to the power of 1, so the bigger degree is on the bottom. Now, as x gets larger, as we saw in a previous video, 1 over 1 is 1, 1 over 2 is a half, 1 over 3 is a third, 1 over 10 is a tenth, 1 over 1,000 is 1,000th. As x gets large, this gets closer and closer to 0. Never actually gets there. It is an asymptote. It is an asymptote emphatically, but it gets closer and closer to 0. So if the higher degree, I don't like bigger, we're going to change it to higher. If the higher degree is on the bottom, it has a horizontal asymptote of 0. Or in other words, the x-axis gets closer and closer to the x-axis. And that's what we saw on this example here, 1 over x squared. We saw it up here for 1 over x minus 2 times x plus 1, and in the original 1 over x here at the top. So it has a horizontal asymptote of 0 of the x-axis. Now please do note that even if you had something like this, if you had x to the 5th power plus 1 over x to the 4th power, please note that even in this case, oops, I did that backwards. If this was x to the 4th and this was x to the 5th and the higher degree was on the bottom, so even though this has a pretty big degree right here, x to the 4th, because it's bigger on the bottom, as these get larger and larger, it still will go to infinity, although not quite as quickly as it would right there with 1 over x. So just be aware of that detail. It doesn't have to be 1 over. It could still be a high degree on top as long as the bottom one has a higher degree. It'll still go to 0. Now the next case is same degree. So when we look at degree, just make sure you remember that if we multiply everything together, what would we get? So that right there is going to give me x squared as the leading coefficient. And right here, I'm going to get x squared as the leading coefficient. These are both degree 2. Now when you have the same degree, top and bottom, your job is to actually look at the leading coefficients. Now each of these is x squared, so that's 1x squared. But you look at the ratio of leading coefficients. And in this case, that's 1 over 1, which is just 1. That is the horizontal asymptote. Now, if this had changed, if I had done something simply like put a 2 outside right here, then this would become a 2x squared, this would become a 2 over 1, and this would become a horizontal asymptote at 2. So when you look at these leading coefficients, the basic premise is, as x gets larger and larger, these two pieces, even though I know there's a lot of other stuff that would come after it if we had actually multiplied all this junk out, ultimately these two pieces would simplify out, and you'd just be left with that. So for really large values of x, those would simplify out, and you'd be left with simply the coefficients, which are whatever they are for that particular problem. So horizontal asymptote of 1, horizontal asymptote of 2. If there had been a negative, we'd change everything to negative. It'd be negative 2. But it's completely dependent on the leading coefficients of those polynomials. Lastly, we have when the higher degree is on top. And so this is kind of the reciprocal of the higher degree on the bottom. And this is an x squared term and this is an x term. Now, granted, there's all this other stuff, but it's inconsequential when x gets really large. These two, the leading coefficients, are the one we pay attention to. And what I know is this: x squared will always be bigger than x, which means this is growing faster than this is growing, which means this will go off to infinity. It will become infinitely big. Now, for this video, we're going to leave it at that. It's going to go off really large, without bounds. It's just going to take off. Now, when I say without bounds, I don't mean there's not structure organization, just that it can get really, really big. But that it will have something in this last case where the higher degree is on top. Oh yeah, I don't like bigger. I'm going to change it to higher. Where the higher degree is on top, it will go infinitely big. But it will be a little bit of structure, and it gets a special name, and it's called an oblique asymptote, and I'll talk about that in the next video. Now, a couple important things to note. While a vertical asymptote is absolute, it will never ever touch the x value where the vertical asymptote is. Horizontal asymptotes are a little bit softer in that regard. By softer, I simply mean in the middle of your graph, so let me just sketch a quick example. In the middle of your graph, there could be some interesting stuff. You might actually have it cross in different places. It may have an x-intercept. A horizontal asymptote is specifically talking about end behavior, as in way out here to the sides for large values and way out here to the side for very small values. So it's possible to have a horizontal asymptote that actually has a value at that asymptote right in the middle, because horizontal asymptotes only apply to the extremes. So don't be surprised if you say the horizontal asymptote is 0 and the function actually has an x-intercept in the middle of the graph. That can happen. So just to reiterate, vertical asymptotes are absolute. You will never have a value on a vertical asymptote. Horizontal asymptotes are soft in that regard, in that they only really matter to the extremes, the outer extremes of the graph. Sometimes in the middle you will have something that crosses that asymptote. It's not an absolute.